Okay, in this section I'm going to be looking at Lenz's law. We'll talk briefly about inductive power transfer, and then we'll talk about the bits that don't involve demonstrations in Lenz's law. So, induction, so this inducing of EMFs and currents, can allow us to charge things without us having to actually connect a wire to them. So in this example, we have a patient with an artificial heart, and we need to get electrical energy into the body without actually having to carry out surgery. So how this is done is that we have use a changing magnetic flux, from an external coil to induce a voltage in internal coil. So that's a coil that's been operated into the patient. This voltage can be used to push charge into battery, recharging it. Electric cars, another issue is that you have to lug around a heavy battery. You can charge it without connections while it's parked in town, so we saw this on page 1. We have a coil under the car park, produces a changing flux. This induces an EMF in a coil in the car, which pushes charge into battery, recharging it. Okay, so we can transfer power from one coil to another without having to have an electrical connection between the two, which is often convenient. Okay, so Lenz's law, we're going to skip this demonstration, and we're going to look at Lenz's law. His name actually was Emil Lenz, and what he did, he stuck a negative sign into Faraday's law, so it looks like this. Negative delta phi over delta t is equal to the induced EMF, and this is the equation that you have in your formula sheet. And what Lenz's law means is that whenever you change the magnetic flux in a loop, you get a voltage, or EMF, that opposes the flux change. So when you push a magnet into the loop, the flux change causes an induced voltage. The induced voltage causes a current to flow. The current flowing in the loop creates another magnetic field. This magnetic field is in the opposite direction to the incoming magnet's field. Similarly, if you try to move the magnet away, the induced magnetic field is in the same direction as the outgoing magnetic field. So it kind of attracts the magnet while you're trying to pull it away, and that also opposes the motion. Okay. We'll skip this. This relates to a demonstration. So here we have an example. We push a magnet into the coil. The increasing flux causes an induced voltage. The voltage causes a current to flow. The current flowing causes the magnetic field, which is the black arrow in here, to oppose the magnet's motion. So if we push the north pole in, then the left end of the coil here will become a north pole. If you try to pull the magnet out, then the left end of the coil becomes a south pole. We can use this to figure out which direction the current flows.